Hello friends, I am Murakami and today we are going to see how to create animated graphs with Matlab for data analysis. So suppose if we are having various data and then how to plot the figures and animation. So we will see. So suppose we are having here data results for a 15 layer laminate. So we are having a 15 layer laminated composite plate and we are having the results using the Exact-3D elasticity solutions and then the Murakami Zigzag theory solutions and the solutions using the Sorrenti-Enhanced defined Zigzag theory. So we are having three theories and all three theories using all these three theories we are having a 15 layer laminated composite plates results. Okay, so we will compare these results and then we will have the animation video for the graphs. So let's start. So I have opened this Matlab code. So let's begin from here. So first of all, we are having a data, the results. This is for the exact 3D solutions. Then the second one is the Sorrenti issue for 15 layer lamina. Then for the Murakami zigzag theory, we are having 15 layer lamina. So now we have stored this data except okay. Then we have also stored y sets here and then labeling we have given here and we will store the videos in terms of MP4. Okay. And then the animate plot, the function is written here. Okay, how to animate and further we will see by running the code. In that comparison, I think there is something Matlab is only when I'm using added zone. Okay, I think I have written map 15 there, so might be I have to change the name. I have to change the name here. Uh, this is the name. So layer 15. Now I think it should work. Cancel it and then I should open it again. I think this one. Okay. Let's open. Now we will run this code. I think it should work now. Yes. So it is showing the transverse displacement curve here. Okay. So here we can see Murakami and Sorrenti's results are coinciding with each other, and the exact solutions are shown on the right side, or the transverse displacements for the top loading when the loading is applied on the top surface of the plate. So asymmetric variation is there. So bottom it's minimum displacement, and as we approach to the top, the displacements are increasing. While in the two-dimensional theory, either Sorrenti's zigzag theory or Murakami's zigzag theory, we will see that transverse displacements are constant throughout the thickness because there was no stretching part considered. I think it's taking a long time, and we can reduce it. We can have 105. Let's see what will happen. we have seen the second in-plane displacements. Okay, so exact three-dimensional solutions is the blue one, and Sorrenti is the green one, which is here, and Murakami is the yellow one. So I think so. At the bottom, we can see a large variations are there. The exact solution is 0.018 almost, while this zigzag theory is becoming a stiffened results, and its displacements are showing much lesser than the exact solution. Let's see at the top what will happen at the top. So I think at top also the exact solution, exact displacements are larger than the zigzag theory showing the displacements. So at top and bottom both the zigzag theory are getting stiffened. Now this is in plane displacements for V or along Y directions. So exact solutions are this. So we can see here at the bottom surface of the plate the in-plane displacements and the zigzag theory, they are much varied from each other, far away from the exact displacement. There are very high error at this end or at the bottom surface. Let's see at the top surface what will be the results. Two definitely. Then the third displacement like this, and the fourth displacements. Now it is, I think it's faster. Okay. We are doing 15 layers, that's why it's taking a lot of time. Okay. So in plane stress also we can see the exact solutions is this blue one, while this Murakami and Sorrenti results are much lesser than the exact stresses at the bottom surface in plane normal stress. And let's see at the top also, I think it is the same. So we can say as the number of layers are increasing, the results are getting steeper. For the large error are there at the bottom surface, as well as we can see here for the top surface also. Now it is for the in-plane normal stresses along y axis. It is also shown here. We can see at the bottom. So it's a large distance, large error at the bottom. The exact solution is blue one. While these both zigzag theory are much farther or lesser than the exact stresses. You can see at the interface also a very large variations or errors are there. Since here we can see pretty much having larger error. So the error are increasing as the number of layers we see increases. So this animated videos also gives a very good idea of how layer by layer the stresses are approaching. Now we are seeing the in plane shear stress. Okay. Again we can see at the bottom the actual stresses from the exact three-dimensional elasticity solution is much larger than the zigzag theory, showing a large error at all the interfaces also. Now we can see the transfer shear stress here, how is the how it is approaching. So this is from the constitutive equation. This is showing that both the Sorrenti and Schwarz exact theory both having a jump at the interfaces and not fulfilling the shear stress free criteria at top and bottom surfaces. So at the bottom we can see it is having a constant values 0.3 and almost 0.35 for the Sorrenti results. While in exact three-dimensional elasticity solutions, we can say that at the bottom of the surface, the transfer shear stresses at the bottom interfaces should be zero, as well as at the top when we will approach, we will see the exact solution is also zero at the top interfaces. So this zigzag theory we can say are having a great error in this. Transfer stresses we can see become zero at the top interfaces. The shear stress becomes zero. While herein we can see that both the theory is having a constant values. Similarly, tau yz also we will see that transfer shear stresses will be zero at the bottom interfaces, while from the Sorrenti and Murakami zigzag theory we can see these are constants. These two results of Sorrenti and Murakami are used using constitutive equations. We are getting the results when at the interfaces the shear stresses are having jumps, not fulfilling the top and bottom shear stress criteria as shown by the exact three-dimensional elasticity solution, where it is zero at the bottom, as well as we will see at the top also it will be zero. Now I think this sigma xz are showing the transverse shear stresses using the integration by integrating the equilibrium equations. So exact dimension solution would be the same. While Sorrenti and Murakami is that we have analytically integrated the equilibrium equations and then solved the results for transverse shear stresses. So also we can see at this end we are seeing that there are large error at the mid span. It's zero, we can say it is having a large error. So it's also approaching. So from the exact 3D dimensional equilibrium equation or integrating that equilibrium equations from Sorrenti and Murakami also we have seen that it satisfies the shear stress free criteria at top and bottom and also gives very close results to the exact three-dimensional solution. But even though it's having some error at the mid span, it's a huge error. Now we will see tau sigma yz shear stresses. So now Sorrenti and Murakami's exact theory was also obtained by integrating the equilibrium equations, which are shown here. So here we are also seeing the transverse shear stresses approaching, and here the results due to the Sorrenti and Murakami's exact theory we can see a huge error are there. Okay, the results that is 0.012, while you can see from here it is almost the results are minus 0.095, sorry, minus 0.002021. So a huge error are there from exact three-dimensional solutions and the both the theory. We are approaching towards end and we approached. You can see at top and bottom the shear stress free criteria is over. Okay, so now we will close here, or we can see that it got stored uh, in a file, I think in the 15 layer, where we can see that the videos are also saved. You can see how it is saved. So videos are saved here. Okay, how these are made. You can see another, suppose this video. So it's showing how the variations are there for plotting the graph animations. So now we will close here. Thank you.